not easy. It's kind of different from anything we've done. But essentially, we have a formula. And this formula, there are various variables, and these variables are in terms of time. And we're typically given some numbers and asked to find one thing. So here is a formula that says the pressure times the volume of a fixed situation is always equal to C, constant. That's all. PV equals C is the formula. P and V, P is pressure, V is volume. So as the pressure and volume change, when you multiply them together, they equal a fixed number. That's what that is saying. So I want you to think of that as being 10 or 1,000,000. Don't think of it as a variable, because it's not. We're told that the volume is 100 units, that the pressure is 160 units, and the rate at which the pressure is changing is positive 40. So the pressure is going to go up. Would you agree? That's what that's saying, right? It's going up by, in the next second, it's going to be 40 units stronger than it was before. And given this formula and only these three pieces of information, we should be able to find out what dV by dt is. Isn't dV by dt going to be negative? Does that make sense? If the pressure goes up, doesn't the volume have to go down so that this product stays the same? So I know I'm going to get negative something. Not that that helps me get the answer, at least I know it's negative. So I'm going to start with the subject formula, which is this guy. And I'm going to differentiate it with respect to T. And we've seen one of these before. Isn't that basically two things multiplied together? So shouldn't I use a product rule to differentiate it? So it's going to be f dash g plus f of g dashed. But what do you get when you differentiate a constant c with respect to t? What do you get if you differentiate a number with respect to t?
0.
And it's 0, yes. Now, if you differentiate this guy with respect to t, you get dp by dt times leave this guy alone. Leave this guy alone and differentiate this guy, and you get dv by dt, and it's still equal to 0. Are you comfortable with that line, where all those little bits are coming from? Now, P is 160. I'm trying to find, trying to find dV by dt. I know this guy is 40. And I don't know yet what V is. Agreed? Is there anything I could do to figure out what V could be?
I thought V was 100.
Oh, my apologies. Even easier. If it wasn't, I was going to plug into the formula and find out what it was. And still 0. So I have 4,000 plus 160 dV by dt. Can you see where we're going to be going in the next two lines? Can you tell how I'm going to use this to find dV by dt? So as long as you do it to both sides, it's okay rule. So I am going to divide both sides, well, not divide, subtract both sides by 4,000 and then divide by 160. And go to my calculator and hopefully get, I think it's -25. That's what the answer I have in front of me says. -4,000 divided by 160. And yep, it is. And for those people who are interested in the units, it's cubic centimeters per minute in this story. But you don't need to worry about the units because WebAssign tells you what the units are. You just need to get that number. That's the same reason why I didn't bother putting the units here. They kind of distract me when I put units in. So I like just the pure numbers. Are we comfortable with that question then? But 4 more to do. Each one gets a little bit different. And towards the end gets really hard. So in question 13, we have a cylindrical tank. So I'll draw a little picture. Helps me anyway. Its radius is 3, so I'll put that in. It's being filled with water at the rate of, in this case, 4 cubic meters a minute. So the rate at which the volume is increasing is 4. And we are being asked to find how fast the height is changing. So can you imagine as the water goes in, there's the water there, right? A second later, won't the water now be here? Aren't we trying to find out that increase in height, right? Well, there are a few things here that I don't have yet, and you might know them, which is great. And if you don't, you go looking for them. Don't I need a subject formula, right? A formula, you know, like this to work with. In this case, it's a volume of a cylinder, isn't it? So the formula I'm going to begin the story with is V equals. Does anybody know the formula for a cylinder?
It's radius of circle times height. Or sorry,
Okay.
the area of the circle. Area of the circle
Yeah.
times height.
You're right. Pi r squared h, right? Area of the circle, pi r squared times h. Now, in this particular cylinder, the radius is 3. Would you agree a cylinder, if its radius is 3, it's always going to be 3 for this story? And so that becomes pi times 3 squared times h. And that's now going to become 9 pi h. Are you happy about how I got the subject formula from this particular story? Volume of a cylinder replacing the radius with 3 because they told me it was 3. Now, differentiate with respect to t. Are you happy with that? Does that seem okay? Now, what do we know? We know this is 4. What are we being asked to find? That guy. Oh, this one came out really easy, didn't it? This one came out almost without any effort at all. What will I do to both sides to find the rate at which the height is increasing?
Divide by 9 pi.
And don't worry about how ugly it is. We want exact values unless they say otherwise. So there's your finish. 4 over 9 pi. Let's move away from volumes of things questions and do a journey. And this one is question 14. And I'm just going to read out each sentence and then try and build a picture. Because in these stories, it helps to draw pictures. Right, at noon, ship A is 140 kilometers west of ship B. So here's ship A. Over here is ship B. So ship A is 140 kilometers away from B. You cool with that? And that's visually what that just said. Ship A is sailing east. So this ship is going to be sailing east. And I'm going to call that X. And it's going to be sailing east at the speed of 30 kilometers an hour. Again, I won't worry about the units. Ship B is sailing north. So this guy, he is sailing north, and I'm going to call that Y. And he is sailing north. That's going to be dy by dt at 25. So you can imagine this ship's going this way and this ship's going that way. You can see as time goes by, aren't they going to be different distances apart? Agreed? So as I read on then, it then says how fast, so they want a rate is the distance between the shapes. Now, if you take this guy here and you join them, I'm going to show the colors here. This guy here and you join them to here, isn't that the distance apart those two shapes are? And I'm going to call that distance Z. And we're being asked to find the rate at which they are traveling apart, which is another way of saying find that guy. And they're asking us to do it when the time is 4. Right, there is a lot going on here. First thing I'm going to try and do is figure out some subject equation that uses X, Y, and Z. Okay. Now, the guy I'm going to do involves me adding some extra lines in, these dotted lines here. Actually, that dotted line doesn't need to go there. It can go there. Right. So you can imagine I slide this up. If I slide this fella up, you basically got a right angle triangle like this. The red part, which is X, is here, right? I'm making this whole thing here the green part. And that's going to be called Y. And this guy here is the Z part. Now there's one other thing that I know, and that's the distance from start to finish is 140. Okay. Now, oops, I put my X in the wrong place. I can fix that. My X is actually here. That's X. And the 140 is everybody from here to here. So what is this side here from here to here? The whole distance is 140, but you've eaten up X of it. So what will this piece be? 140 X, what's this piece?
$140 minus X.
Okay. A little bit of a mess, so I'm going to draw the essentials. This is Z, this is Y, and that guy is 140 take away X. I have a little right angle triangle. I'm going to use that to get my subject formula. And I'm going to use, who do you think I'm going to use? I'm not going to use similar triangles, that's for sure. Who am I going to use this time?
The Pythagorean theorem?
Yeah. So Z squared is going to equal Y squared plus 140 take away X squared. This is one ugly equation, but would you agree it connects X, Y, and Z together? And I need that. This guy is going to be Z squared. This guy is going to be Y squared. I'm going to FOIL this horrible thing out. So 140 squared is 19,600. Take away 280x plus X squared. There we are. Whew. So far, so good. Now, what kind of numbers do we know? Well, I know quite a few things. I know, for instance, dx by dt, it's 30. I also know that dy by dt is equal to 25. Since t is equal to 4, right? If this guy is traveling at 25 miles an hour for 4 hours, that makes y equals 100 miles. 25 times 4. This distance here is 140 take away x, right? This distance here. And he is traveling at 30 miles an hour. So in 4 hours, that's 120. So 140 take away the 120, that leaves me with 20. And if I give myself enough room, How am I going to find Z? I know that X is 100. I know that this guy, well, actually, I know what X is. I should put that in. X is 120. And I know this guy in here, that's the 20. And I know Y is 100. I know X is 120, but I know this is 20. I know Y is 100. How will I find Z? Because I need to know that as well before I do anything else, and then we're ready to go.
The
If this is,
Pythagorean theorem.
yeah. So Z squared is 100 squared plus 20 squared. Z squared is 10,000 plus 400. Z squared is 10,400. So Z is the square root of 10,400. Are you not glad you only get one of these? Right. All the numbers that we need are over here now. So 10,400. So let's do the differentiation. If you differentiate this with respect to t, you get 2z dz by dt. If you differentiate this guy with respect to t, you get 2y dy by dt. If you differentiate a number, you just get a number. If you differentiate this guy, you get negative 280 dx by dt. And if you differentiate this guy, you get 2x times dx by dt. So I've differentiated every single thing with respect to t. I'm now going to put in these numbers into here and see what we have. Z is the square root of 10,400 times dz by dt. 2 times y is 100, dy by dt is 25, 280 dx by dt is 30, 2 times x, which is 120, times dx by dt, which is 30. So I now have the square root of 10,400 dz by dt is equal to that ugly thing. So let's see what that ends up being. 2 times 100 times 25, take away 280 times 30, plus 2 times 120 times 30. And so it looks like that's 3,800. Hopefully. Almost done.
Did you divide the 2 out? The 2z?
Not yet. And I haven't quite done that yet, but that's what I should do now, shouldn't I? Divide both sides by the 2 z's, which is this thing. So got this number, divide by, put a bracket around it, 2 times the ugly value for z, which is square root of 10,400, and the answer I get is about 18.6. And if you want to know the exact answer, because it's in front of me, it's 18.631. And I believe the units are, well, kilometers per hour. Not meters per hour, number is the same. That is one ugly equation from start to finish. That would be a kind of ultimate version of that, you would think. But there's actually one even uglier than that one. But I am going to do the solution to the ugliest one of them all on a PDF, and I will just put that in notes sometime in the next few days for you to see it. And you might say, well, why don't I just do it in class? It'll take me about 25 minutes. And we don't have 25 minutes. And I would like to kind of move on to the next topic, because It's a lot of time for one question. So the one that we're missing is a cone being filled up with water, and we're going to find the rate of change. It's the last question in that section of homework. So you should be able to look it up later yourself. Right, so section 310 now. The linear approximations is what we're doing for today. Approximations and differentials. Linear differentials, linear approximations, I should say, have been around for a long time. They almost became bread and butter when calculus first got invented, because what they allowed us to do is to get an approximation to the value of a function. Right. Can you imagine a time, I know it's hard to believe, but can you imagine a time when there was no computers and there wasn't even electronic calculators? So every single calculation had to be done by hand. Imagine a time when that was true. And it was true when calculus first came out, right, in the late 1600s. And so what they had to do is they had to find workarounds for getting the value of a function at a particular point that would make it relatively easy to do, but still be pretty accurate. So it's not a perfect fit, but it's an approximation that's pretty good. So let's give you the theory behind how it works. Imagine you've got your classic y equals f of x. And let's suppose I'm interested in a point whose x coordinate is a. And I find the tangent line. That's this line here, right? See the tangent line? If you zoomed in at that point there, can you imagine that the curve might look like this and the tangent line might look like that? For that small interval of values, roughly somewhere between here and say here, wouldn't the equation of the straight line be a pretty close fit to the curve? Would that seem reasonable, right? For small pieces, you could do that. And we have a formula called the linear approximation function. And what that essentially does is it gives you a linear equation, right? A 4x plus 7 kind of thing. And it allows you to find a straight line, essentially the tangent line, that you can use close to the value of a to approximate the function. And the linear approximation function, Lx is its typical name, of a function y equals f of x close to x equals a is, and here we go, L of x f of a plus f dashed of a x take away a. So the linear approximation function is this guy, right? The value of the function at a plus the derivative of the function at a times x minus a. Can you imagine these are going to be numbers? And so when you're finished, you're going to have L of x is 3 plus 2x, or 0.7 plus 5x, things like that. Let's show you in operation. Suppose I want to know the value of the square root of x, and I want to know values of it close to a equals 9, right? So I'm going to use the linear approximation function to come up with an estimate for what the square root of x is. And as long as I keep my x's close to this number, it should be a pretty good answer. So I should be able to use it for things like 8.1 and, you know, maybe 8.7, 9.1, 9.2. Well, I need to differentiate this function, so I'll call it x to the half. I'll find its derivative, which is multiplied by the power, reduce it by 1. I'll do some style points on it. Hopefully I've done this kind of derivative enough times to understand what I just did there, right? Are you comfortable that is the derivative function at any given value of x? Now, since a is 9, the linear approximation function is the value of the function at a plus the derivative at a, x minus a. Well, the value of this function at 9 is the square root of 9, which is 3, plus or minus, oh, not plus or minus, plus the derivative, which is what, 1 over 2 times the square root of 9, x minus 9. I'll just tidy that up a little bit. 3, that's a sixth of x take away 9. A couple more lines will be there. Distribute the sixth, so 9 sixths is 3 halves. And I get 1/6 add 3 halves. That is my linear approximation function for the square root of x, close to a equals 9. Let's take it up. I would like to get an estimate for 9.1, right? The square root of 9.1. Okay. The correct answer, at least to 6 decimal places or so, is on our calculator. So this will give us a comparison to how good it is. The correct answer is 3.016620,626. Agreed? Take about 8 decimal places, actually. I'm going to use it for this function, right? So I'm going to do the linear approximation at 9.1. So that's going to be 1/6 of 9.1 plus 3 halves. Okay, let's see if you're a gambling person. Would you be impressed if this was good to 2 decimal places? 3 decimal places? How many decimal places? Rachel, put you in the spot, pick a number. How many would you think it was going to be, or how many would you be impressed if it was? 3 decimal, 4 decimal, 1 decimal place? What do you think?
At least 4, maybe more.
Right. So Rachel's going to be impressed if it's 4 or more. Vanessa, would you be impressed if it was less than that? If it was still good to 2, would that still be okay?
I'd be surprised if it was more than 4. Yeah.
Okay. Well, let's find out. On our calculator, it's 1/3, 1/6. So I guess I could just say 9.1 divided by 6. Add 1.5, and the answer I got is 3.0166. I'll stop counting there. Hey, pretty good. Now, can you imagine how that would be useful if someone in engineering in the 1690s was trying to find the square root of 9.1 and they didn't have a calculator because they weren't invented yet? Couldn't he use that number there and feel pretty comfortable that he got the answer, right? In fact, they probably wouldn't need that degree of accuracy because in those days, you know, things were kind of, as long as the bridge didn't fall down, people were pretty happy, right? You didn't need to be like 1,000th, you know, accuracy, right? Nothing was ever made to that kind of accuracy, I guess. Maybe watches, but they were the only things. Impressed? We now have a way of estimating the value of any function as long as you stay close to this guy, right? Let's try a new function. Keep it simple. Sine of x. And we're going to do it close to 0. So the derivative is the cosine of x. And we should be ready to go then. Linear function is f of a plus f dashed of a, x take away a. That's going to be the value of the function at 0 plus the derivative at 0 times x take away 0. Okay. Oh, the sine of 0 is 0. The derivative is the cosine of 0. So the cosine of 0 is 1. Wow. That's a very, very simple linear function, isn't it? It's just basically y equals x. Let's try it then. Let's see how good it is. In the 1720s, I had to find in radians the sine of 0.123456, right? I'm making those numbers nice and easy because that way we can compare it good. According to the linear approximation function, shouldn't the answer just be 0.123456? Agreed, right? L of x is x. Okay, Nick, how many degrees? How many 2 decimal, 4 decimal? What do you think it's going to be this time? Come on, commit.
All right, we're gonna say that it's better than last time. We're gonna go to 6.
Wow, you're a hard task, Scott. Let's see if we can get 6.
Well, you set the standard pretty high with 4 right off the bat.
You're right. My own fault. Oops. Make sure you're in radians. Calculus works with sines and cosines only in radians. That's just the way it works. So now I'll do it again. So it's going to be the sine of 0.123456. And the answer is 0.1231. I can stop counting now. Okay, well, 3 decimal places is still pretty good, right? Can you see there might be a use for this as a rough and ready way of calculating something without having a calculator, right? It's lost a lot of its importance because nowadays don't we have calculators, so there's really very little need for us to do approximations. But it is a kind of cool thing, nonetheless. Any questions about that? In a lot of ways, isn't that just so much nicer than related rates? It's so much easier to calculate and to use. So some things get hard and then it gets easy for a while. So hopefully that's your opinion as well. Let's just show you one. Which one will I pick? This is question 2. The function is the cube root of x, and it's to be near 125. Okay. So I need to find this guy's derivative. In other words, are you happy about turning into a fractional power so I can differentiate it? That's second nature now. If you want to differentiate this fella, you need to write it that way. Its derivative is going to be multiplied by the power and reduce the power by 1. And then we have to do style points on it. So it's going to look like that. And then to finish, it's going to look like that guy, right? And so the linear approximation function, f of a plus f dashed of a all over x minus a. So it's going to be the value of the function at 125 plus the derivative at 125 times x take away 125. Okay, the cube root of 125 is 5. This guy is 1 over 3 times the cube root of 125 squared. Good grief. Well, that's 5 times 5, so it's actually just 25. Again, I'm probably putting more lines than you would want or need. Okay, we're almost there. All I'm going to do is combine these together, and that's what fractions are for. So here it goes. Calculators are for. 5 take away 125 divided by 75, and then just turn it into a fraction, and it's 10/3. So it's 1/75 x plus 10/3. And that's all they want, so we're finished. I mean, they could have said, well, use it to estimate the cube root of 126, you know, something like that, but they didn't, so we won. Any questions about that? Are we comfortable? Okay, that's good. Now, the next question is a linear approximation question. It's just phrased in a funny way. It's question 4. It says verify that the given linear approximation, I always put the word close to, a equals 0. And then you can use your graphing calculator and do stuff like that. That would be Desmos. And the function that we're meant to show is that 1 plus 5x to the negative 4 is approximately equal to, that's what the funny little squiggles lines look like that. So let me tell you what they've told you. They've told you that that's the linear function, and your job is to prove that that's the linear function. Right? So this is the function you start with. Prove that this is the linear function of that guy close to there. So the function that we're going to be approximating is this fella. I would call him 1 over 1 plus 5x to the 4 if I was doing any calculation. But if I'm differentiating, this is the way I would want it to be written. So let's differentiate it. Multiply by the power and reduce the power by 1. Anything else I should be doing when you differentiate this? Think chain rule. What should I finish with?
Multiply
Inside,
by the derivative of the inside function.
which in this case is 5. And so that would become negative 20, 1 plus 5x to negative 5. There's some little squiggles from before. Negative 20 over 1 plus 5x to the power of positive 5. So there's my derivative. So the linear approximation function is the value of the function at a plus the derivative at a, x minus a. In this case, it's 0 that we're going to be doing it on. Well, the value of the function at 0 is basically this function, but if you write it that way, it's easier, because if you make x 0, it's just 1 over 1 to the 4, which means it's still 1. And the derivative, well, if you plug 0 in here, you get negative 20 over 1 to the 5, which is just negative 20. Or basically, negative 20x. Hey, we've proved it. Now, there is a second part to that question, which talks about how good is this approximation? And they phrase it by this. It has to be within 0.1 of the correct answer. and they want to know what range of x's can I use this function so that it's within 0.1 of the correct answer. And that's really just a Desmos thing. So if you, while I'm getting myself sorted out, why don't you put your last name in for attendance if you haven't already done so? I should be ready shortly. So I'm going to be putting in the original function then, y equals 1 plus 5x to the power of -4. That's the original function. And that shouldn't be a capital, so I must have my caps lock on. That's cool, got that. And then I'm going to type in my linear approximation function, which is y equals -20. Well, let's put it in the order I originally wrote it. 1 take away 20x. Okay. Now, we are meant to be doing this close to 0. Can you see that this scale is just horrible? You can't really see what the heck we're doing. So I'm going to go over here and I'm going to choose my x-axis to be close to 0. So I'm going to do -1 to 1 right now. There. So far, so good. Right? Now, if you look at the linear approximation function and the curve one, can you see that you have to zoom in quite a while, right? Before they're pretty good. So would you agree somewhere around about here to here, right, is roughly where I want. Now I want to be within 0.1 of the correct answer. And that's going to be a little bit tricky. How do I figure out what that looks like? Well, I'm going to do a couple of little abbreviations here. That guy is going to be now 0.1 and -0.1. So I'm going to change my x values from -0.1 to +0.1. And I chose the wrong guy there. Shooting space. I'll make that one. I'll make that, what would that be? 0.6. That's not the one I meant to change anyway. It's this one up here I wanted to change. So it's going to be -0.1 and +0.1. Right, click off that, move it up a little bit. Yeah, I'm looking pretty good here. Now I'm going to take this function and I'm going to add, oops, 0.1 to it. Not 0.1, was it? Oh, they wanted within 0.1, didn't they? Okay, so I do want that. And I'm taking that function and subtract 0.1. So I need some different colors here. So I want to change this one to green. Right. And I'm going to zoom out a little bit. Our approximation is the blue curve. You see that guy? These green ones are basically error bands, right? Plus or minus 1.1 on the thing. So what I need to do is I need to, let's see if I can hide that one. Hide the red one. Don't I just need to know where that guy is and where that guy is? And so there's your range from -0.018 to +0.22. As long as you keep X in that range, you will be within the accuracy that they're talking about. I can't really do more. Well, I guess I could a little bit more. I just keep changing my windows. I hope I've changed it enough. There. Can you see the guys I'm talking about where it leaves The green road is safety. The minute you leave it, that's the last place you can use. Can you see what I was getting at when I was talking about the negative x, this guy? And then over here, the other x. Now, if you wanted it to be even more or less accurate, wouldn't you just say, if you wanted it between 0, 1 and 0, 1, wouldn't you have to zoom in? But eventually, it would be at that point there, roughly, and at that point there. Well, that's all we have time for today. So bye-bye for now. Hopefully you've already put your name down, and I will see you tomorrow. And keep your eye open in the next couple of days for a solution to the Cohen question from related rates, so you can have a look at it.
Thank you.
You're welcome. Bye-bye, guys. I'll hang about for any questions as always. Are we good, Rowan? I will assume so. So bye-bye.